Parasitic capacitances of MOS transistor. MOS transistor is a 3-terminal device or 4-terminal device, that is gate, source, drain and bulk. It has 5 parasitic capacitances: gate to source capacitance, gate to drain capacitance, source to bulk, drain to bulk and gate to bulk. So this is the structure of an NMOS transistor. When the gate to source voltage is greater than the threshold voltage, there is positive charges present on the gate, that's shown here. We have a dielectric region of thickness T, and then when UGS is greater than threshold voltage, we have the charges, that is the free electrons in the channel. So this forms a capacitor. Basically, capacitor has 2 terminals, 2 plates separated by a dielectric of thickness T. So the capacitance C will be equal to epsilon naught r times area of the plate divided by the thickness. So in this case, COX is the capacitance formed in this region, and then there are free electrons, we have a depletion region, and then we have free positive charges in the P substrate. This forms a capacitance. Since we have 2 plates, it resembles 2 plates separated by a dielectric, so this capacitance is called CD. Now coming to the gate and the source terminal, because of under diffusion, there is some part of source which is coming above the gate, so that forms a capacitance, and it is called as CGS overlap. This is the capacitance formed here. And in the drain as well, due to under diffusion, some part of the drain comes directly above the gate, and this forms gate to drain overlap capacitance. Then we have a source region and the bulk region. Source is N plus, bulk is P, so this forms a diode, and because of a diode we have a depletion region present, and this forms a capacitance called as source to bulk capacitance. Similarly, we have drain to bulk capacitance. So in this diagram we can see the capacitances which I explained, that is COX capacitance, CD capacitance, gate to source overlap capacitance, gate to drain overlap capacitance, and then we have the source to bulk capacitance and the drain to bulk capacitance. So the oxide capacitance, that is the COX capacitance, what is it dependent on? We know the capacitance C equals to epsilon naught epsilon r A by D. Where A is the area of the capacitor plate and T is the thickness of the dielectric. So when we see COX capacitance, area of the capacitor plate is nothing but length of the channel L into the width of the gate. So it depends on W and L. COX equals to COX dash times W times L. So here the thickness T is taken over to COX dash because the thickness of the dielectric, this thickness is technology dependent and it cannot be decided by the designer. So here COX dash is nothing but epsilon divided by TOX. This is set by the technology and it cannot be decided by the designer. Next we have the depletion capacitor. Depletion capacitor is the capacitor formed here between the channel and the P substrate, and it is given by the above equation. CD equals to square root of Q times epsilon of silicon into N sub divided by 4 phi F times W into L, where N sub is doping concentration of the substrate, phi F is Fermi potential, epsilon SI is dielectric constant of silicon. So here again the depletion capacitor is dependent on the width in times length. Overlap capacitors, the gate to source overlap and gate to drain overlap. Because of the under diffusion we see this capacitance, and this capacitance, the length, this distance, that is the overlap, this cannot be decided by the designer. It is due to the under diffusion. However, the width of the capacitance plate can be decided. So GS overlap equals to CGS naught times width. As also the gate to drain overlap equals to gate to drain 0 times width. So this equation means that the designer can choose the values of W and decide the gate to drain overlap capacitance or the gate to source overlap capacitance. Next is the drain to bulk and source to bulk capacitances. This is formed because of the diode formation, that is the PN junction between the N plus and the P substrate, which can be seen here, N plus and P substrate region. So we have a diode formed. Because of the diode we get a depletion layer, so it resembles a capacitor. We have positive charges, negative charges separated by a depletion layer, so it resembles a capacitor. That is represented by C source to bulk and C drain to bulk capacitances. I will explain how depletion capacitors due to the PN junction between source and bulk or drain and bulk is formed. Let us see the three-dimensional structure of the drain or source. So here we have, it is a cuboid with 6 sides, that is the front side, the back side, the bottom plate, the top plate, the right side plate and the left side plate. The bottom plate capacitor is this one, its length is LD and width is WD. So the capacitance CA equals to CJ times AD, where A is nothing but the area of the bottom plate, that is nothing but length times W. For the remaining side plates, that is the front, the back and the right side plate and the left side plate, the equation is CSW equals to CJSW times PD, where PD is the perimeter, which is equals to 2 times WD plus 2 times LD. Therefore, the drain to bulk capacitance equals to CA plus CSW, which equals to CJ times LD times W plus CJSW times PD, where PD is the perimeter of the drain. Next is overlap capacitor formed due to overlap between the gate and the bulk. So we have the gate to bulk overlap capacitors, which is formed here, and this depends upon the length of the channel L. The gate to bulk capacitance and the gate to bulk overlap capacitance is of not much importance because its value is very less. These parasitic capacitances are dependent on the operating regions of the MOS transistor. In the sub-threshold region where UGS is less than UT, there is no inversion layer so there won't be a oxide capacitance, as there is no channel formed between the source and drain. In linear region, UGS is greater than the threshold voltage and UDS is less than UGS minus UT. So there is a channel formed, and this channel is a continuous channel. Therefore, the capacitance CGD or CGS equals to 0.5 times COX plus CGS overlap in linear region. Whereas in saturation region, the channel is not uniform, and this results in no channel near the drain, as CGD is lesser than the threshold voltage in saturation region. Therefore, CGD in saturation region equals to only CGD overlap, whereas CGS equals to 60% of COX plus CGS overlap. Summary of parasitic capacitances of MOS transistor. The gate to source capacitance, it depends on the operating region. In linear region, gate to source capacitance equals to 0.5 times COX, that is the oxide capacitance, plus gate to source overlap capacitance. In saturation region, CGS equals to 0.6 times COX plus gate to source overlap capacitance. In CGD is the next capacitor. It also depends on the operating region. In linear region, gate to drain capacitance is 0.5 times COX plus CGD overlap. In saturation region, CGD is a very low value, which is equal to gate to drain overlap. This is generally 2 orders of magnitude smaller than CGS. And we need to remember the dependencies of the capacitance on the width and length. Here we can see COX is dependent on the width into length. CGS overlap is dependent only on the width, and also CGD overlap is dependent only on the width. The next capacitance is nothing but the source to bulk and the drain to bulk capacitances. They are given by this equation, which is equal to CSP, that source to bulk capacitance, equal to CJ, junction capacitance, times area of the source. It is equal to width into length of the source plus C, junction side wall capacitance, times the perimeter of the source, which equals to 2 times W plus 2 times length of the source. Similar equation is for the drain to bulk. And the order of magnitude, generally C source to bulk is smaller than gate to source voltage capacitance by order of 1 order smaller in magnitude. We need to remember this. The last is the gate to bulk capacitance. This capacitance depends on the width into length. The gate to bulk overlap capacitance depends on the length, and it is generally a very small value, so it is often neglected.